Hello guys, this is Val from Core Conservation, and this video is going to be about the magnetic DPC. The video is going to be broken down into several chapters or sections which are going to be built on top of each other, so it's advisable to watch from beginning to end to make more sense. So the video is going to have the following main sections. First, I would like to talk chapter 1, I would like to talk about what this magnetic damp-proof course is, kind of what's the purpose of it. Second, a bit of insight into the historical background of the technology, how it has been developed, how it came about. Third chapter, I would like to talk about and go into a bit of details about the research, what research has been done about the technology and what research has not been done and why. Fourth chapter is going to be the working principle, how the technology works, and this is going to be an interesting part because we are going to go into, in order to understand how this can work and what does it do, we need to understand basically what rising damp is. And there's quite a lot of misconceptions out there, so we're going to actually go down into the scientific background of the problem, give you some data. Then we are going to go into the breathability, the topic of breathability, and look into the two main variables that control the breathability to make walls more breathable. And once we know all this, we are going to look at the magnetic damp-proof course, how everything is coming together and how the magnetic damp-proof course system can dry the walls. And finally, in the final chapter, is going to be some FAQ, frequently asked questions, about safety, certification, recognition, and so on, covering the most important or most relevant questions about this technology. First question, what is a magnetic damp-proof course? The magnetic damp-proof course is a new way of dealing with rising damp. Before that, pretty much every damp-proof course solution was trying to block the rising damp. If you look at the historical development of damp-proof courses, and let's show you here, the first in time were the physical damp-proof courses. These have been invented by the during the Victorian times, and then various type of bricks, glazed bricks, or asphalt, or slate bedded in cement, and so on, has been used to stop the ascent of water. The problem with this is that once you apply these damp-proof courses, after about 60, 70, 80 years, it will break down and then the problem comes back. So as a result, after the original damp-proof courses started breaking down, then retrofitted physical damp-proof courses were another way of dealing with the problem. They applied special steel plates, for example, which stop the problem. The problem of this method is that it's very, very invasive, and as a result, it's not really suitable for listed buildings or pretty much any building which is of historical importance. In order to improve and to make these damp-proof courses less invasive, because all these technologies are kind of built on each other, and each damp-proof course technology was superseding the previous one, was trying to improve in efficiency and also to try to decrease the amount of damages which have been done. So the next one, which is kind of mainstream today, are called the chemical damp-proof courses, chemical injections being administered to the wall, and the chemical injection spreading in the walls supposed to stop or block the rise of water. Then also there were, in the 80s, 90s, the electroosmotic damp-proof courses, where an electrical wire was drawn at the base of the wall, and by creating a reverse electrical field inside the wall, they tried to reverse the rising damp and dry the water out, down. And finally, this leads us to the magnetic damp-proof courses. Now, the magnetic damp-proof courses work completely differently. Instead of trying to block the rise of water by physical means, by putting something into the walls, by understanding what makes water stick or bond to the walls, the magnetic damp-proof course prevents the bonding of the water inside the wall capillaries rather than trying to block it. And we're going to get into the science a bit later in this video. Second question. Let's look now at the historical background of the magnetic damp-proof cores technology, how these have been developed. The technology goes back to the 1980s, 1990s, and here on the screen we can see some of the patents which have been filed along the years. This is just a few of them which I handpicked here, and it can be found on our website. The earliest I found, it dates from the 1980s, and if we click on it, because these are live links, we can see the original patent description on Google Patents, US patent number, apparatus for the dehumidification and drying of damp structures, and we have the English translation here, and so on. Water is a polar molecule, which means that the H2, the water molecule, has a positive and negative side. It's made of oxygen and hydrogen, and one side of the water molecule is positive and the other side is negative. It has a polarity, that's why it's a polar molecule. It means that the water molecule can be affected and influenced by various electromagnetic fields. This has been observed. This was something which engineers have observed going back 20, 30, 40 years. And they have devised various solutions in order to reverse the water rise inside the walls. There are a number of patents filed. As you can see, some of them are powered devices, some of them are unpowered devices. Probably most of these have been never became commercially viable product, or never have been manufactured commercially. But the research trail is there, is available. You can see this is a passive electronic device against capillary rising walls, as it says. Then we have another one with electromagnetic device and so on, this using electromagnetic pulses and so on. So there's a whole research trail here. Engineers claim that this is occurring, and then they have created these devices. This leads us to the next question about kind of the research background of this technology. Now, the research background of the magnetic damp-proof cores is composed of two different and related research lines. First is the hardware, or researching the technology. Various engineers, clever engineers, mainly electronic engineers who were good at microwaves and various electronic circuitry, they have observed obviously that the water molecule, being a polar molecule, can be influenced by various electromagnetic fields, and created these devices. Probably from building conservation viewpoint, this is the less exciting part. It's just a contraption, just a device which basically engineers claim that it does this and that's it. The more interesting part of this technology is the second research line, which actually has to do with the wall fabric. And the question which are always being asked, or anyone would ask, basically, okay, we have these little boxes or whatever, but how these affect the wall fabric, and even quite puzzlingly at a distance. So we have this magnetic unit or whatever on the wall or on the ceiling, looks like a beehive or something, and then it's sitting there, or it's screwed onto the walls, and what's going on? How can affect the water movement at a distance? And that was the challenging part, and because this second part of the research hasn't been completed until recently, or hasn't been really dealt with recently, that's why this technology has been left kind of on the sideways, on the sidelines of science for several decades. No one was really interested in the electronic aspect of the technology, because it's a geeky subject about kind of what circuitry goes into these boxes. But the question was how these things can affect the wall fabric. And in order to answer that question, we need to understand and need to go into a bit deep into the subject of rising damp, the topic of rising damp, and understand what it is before we can discuss how we can overcome it and how can we reverse it. And looking into the topic of rising damp, it's probably one of the more controversial topics of building conservation. It is not complicated, but it's controversial. And we spent quite a bit of time researching this phenomenon, going back really to basics. And I have a presentation here. I will just show you a few slides. And here on the screen you can see a slide from one of the presentations I have done. And here just shows you, gives you a bit of the flavor, some of the research we have done during the past few years. We actually have taken the whole concept of rising damp back to the very, very basics, to taking one single brick, putting it in a tray, attaching some sensors to the inside of the brick, to the outside of the brick, putting some water and monitoring whether water will rise, to what height, and what's going to happen. So in a strictly controlled lab environment, which was well heated, well ventilated, non-condensing, so condensation wasn't an issue here. We wanted to see the basics, how water rises in the building fabric. Then we went one step further. We created a small wall. We added a bit of soil here, and then we monitored the rise of water through a more real type of scenario when we have a soil. Then we started building little walls, and then finally we went to real buildings and verifying the lab findings on real buildings. And we wanted to understand what the main stages of rising damps are, what additional phenomena accompany the movement of moisture, and whether what we see in the lab applies and is true in real buildings. And the answer was yes, it was. And if you want to understand rising damp, the fundamentals of rising damp, we need to go back to nature. And here what we see here is the water cycle, which is probably taught at primary school. We have the water makes an ongoing cycle in nature, rainwater falls and vapors rise. So we have two elements of these two main arms of the water circulation. Rainwater coming down in liquid form, collecting in the ground, then evaporating upwards as vapors. And what is interesting and what is important, that only vapors rise. So if we build a wall onto the soil, and bear it in mind that the soil is always damp to some extent and is always evaporates upwards, then the moisture evaporation is going to occur inside the walls. The source of the moisture is the ground, typically from under the buildings, and we are going to have moisture evaporation occurring upwards. Now what is important to understand, this is not capillary action. Because if we look at the wall fabric, or we look at a wall in a normal scenario, we have the wall here, and then we have the water table under the wall. And in a majority of cases, or in a typical case scenario, the liquid water table is under the wall by quite a bit. And the point is that the water table is not going to touch the bottom of the wall. There's no liquid water at the bottom of the wall. And yes, in certain times of the year, typically in the winter time or after heavy rain or in a floody period, the water table can rise to an extent to have liquid water at the bottom of the walls. For example, like we have Venice, where the building is sitting in liquid water, then yes, we obviously have rising damp and we have capillary action. But in the majority of the cases, the water table is down there and we don't have liquid water to cause capillary action. So the only thing which is going to rise inside the brickwork are vapors, which are in this zone, the orange zone. And then what will happen is the vapors rising, because we are talking about extremely small capillaries, which have micron or anyway very small sizes. Very small amounts of vapor will saturate it and is going to reach 100% relative humidity. And because we have an ongoing pressure, we have the rise, it just keeps, the vapors are keep pushing, it just keep rising and rising. We have this pressure situation from the ground. As a result, the water will liquefy and is going to start condensing, which is going to lead us to an ongoing, to a phenomenon, a long-term phenomenon. If we analyze the capillaries, we have the dry capillaries here, vapors moving into the capillaries. We have one layer of water, then we have two, and so on, eventually leading to a liquid film of water on stage 4, which can lead to non-saturated or saturated capillary flow. So the point is that from vapor movement we can get liquid water inside the walls, but in a majority of cases, apart from when we have a lot of rain and we have flood, the capillary action which occurs inside the walls is indirect, is occurring through a vapor phase. And if we revisit this sketch here, basically what will happen inside the wall, we have the liquid water table, then we have this vapor area which can eventually lead to liquid water or vapor and liquid mix, and this is rising damp. Just one final comment here. When we look at the capillaries and we notice this liquefaction process here, this doesn't occur because of the wall is too cold. It doesn't occur because of the cooling effect of the wall. We have done extensive testing, putting sensors deep inside the walls and putting sensors outside of the wall, this in the middle of the winter, which is basically the walls are a lot more liable to condensation. And then what we found is that inside the walls, the temperature of the wall fabric is about 2 to 3 degrees warmer than the temperature of the surface. This at first sight sounds a bit counterintuitive. You think about this, oh well, you know, this is, the walls are damper inside the wall, so the wall should be cooler and it condenses because it cools down. But no, it's not, because the walls have a thermal mass, and the coolest part of the wall is going to be the evaporative surface, because evaporation cools the surface. And we put the sensors inside the walls, and we were surprised to see that pretty much consistently the core of the wall is always warmer than the surface, and the surface is the coolest part. So pretty much this phenomenon occurs because of pressure. We have the moisture keeps rising from the ground, just keeps evaporating into the breathable wall fabric, and as a result the void is going to be filled with vapors, and this will make the water condense, and this occurs because of pressure. So that's pretty much the mechanism of rising damp. The primary mechanism is vapor movement. The source of the moisture is the ground, is coming from the damp ground. And this is a self-sufficient mechanism. This will vapor rise and then liquefaction inside the wall fabric is self-sufficient. It has nothing to do with water ingress inside the walls or liquid or rainwater. This will occur even if the building is very, very well kept. It will occur if the building is very, very well pointed and the building is maintained. It's pretty much, it's an age thing. It's a complex scenario. And once we reach this liquid film along the capillaries, as is shown here on stage 4, then salts start moving into the wall fabric, liquid diluted minerals from the ground, they start moving, which crystallize on the surface. And the salt movement will kick in additional mechanisms and will accelerate the whole process. I will not go into the scientific details too much, but the point is that we have the water rise through vapors, and then we have the effect of salts, and there are several mechanisms at play leading indirectly to capillary action. That's why we can see rising damp on internal walls, which are completely sheltered from rain. There's no way of being any other water ingress there, and it occurs because the vapor rise, the salts rise, and they create the problem overall. This kind of summarizes the 3 types of main water sources in all buildings. One is the falling arm, the liquid water coming down, and can take many, many forms, but it's basically this rainwater ingress, and it affects old and new buildings alike, and it's very, very copious, it's very abundant, it creates fast damages. The second moisture source is the rising damp or soil evaporation, the vapors from the ground rising into the wall fabric, creating the problem of rising damp over time, and that's a self-sufficient mechanism. And third, we have the condensation here, and condensation occurs when we have vapors turn into liquid water because of either cooling or too much moisture. I'm not going to go into condensation. I'm going to do a video about condensation, the 2 main reasons behind condensation. At the moment, probably it's not that important. The next thing which we need to understand and look into is the topic of breathability, a concept very important in building conservation. While a rising damp is a moisture source and it makes the wall fabric damper, then breathability, it means that the fabric has an open pore nature and it allows the moisture to leave the fabric naturally. And it's a common assumption is that if we keep the wall fabric breathable, then we don't have a dampness problem, because moisture can go in and can go out. So as long as the fabric is breathable, dampness, it's not a problem anymore, because it goes in and it goes out. And this is by far not the case. And the research what we have done on this front, it was actually quite interesting and it was an eye-opener to us. And I would like to cover some of these basics and demonstrate and show you why and what are the limitations of breathability, because there are additional mechanisms here at play which make breathability a limited dehydration mechanism. Breathability is controlled by two main variables. The first one are the moisture barriers. So what we have here is fundamental. We have a wall. If we make a wall fabric non-breathable by applying, for example, modern concrete or cement or plastic membranes or non-breathable paints on the surface, all these materials act as moisture barriers, which means that if we have an otherwise breathable vapor permeable wall fabric and we apply this moisture barrier on the wall, shown in gray, for example a cement render on the wall, that's going to affect the movement of vapor, is going to make the moisture accumulate inside the wall fabric and is going to lead to dampness problems. This is very well known, it's very well documented. As a result, it's important that as part of the maintenance of all buildings to stay away from non-breathable materials or moisture barriers. However, an interesting part is here, we also have a concept called surface energies. Now, surface energies are tiny electrical charges inside the masonry. This is not something you add to the masonry like the moisture barriers, you know, that we put something, cement, render or plaster on the wall and you can remove it. No, surface energies are natively inside the building materials. Fundamentally all matter, pretty much anything, brick, stone or even plastics, whatever, all matter is made of pluses and minuses. As atoms and molecules are made of pluses and minuses. So all solid materials, they have some sort of surface energy or surface charges, are very tiny electrostatic-like charges which are available. And very often when in bright sunlight, when you see the dust particles flying everywhere and the dust sticking to surfaces, is because of these surface energies. The solid materials, they attract these tiny light particles and they will attract it and they will make it cling with electrostatic charges. And these surface charges can be found on the surface of each pretty much solid material and also liquids as well. And these surface energies are shown with these little red pluses inside the wall fabric. And because the water molecule, as mentioned earlier, they are polar molecules, they have a positive and negative side. So they are like tiny little floating magnets. When the water molecules are flying inside the wall fabric, they're going to attract it, and the water molecule is just going to be plastered against the solid wall fabric. And let me just show you here, I think I have something here. That's exactly what I was looking for. So if you look here, we have, let's say, we have on the right hand side, here is the ground, and this is on the left hand side, we have the upper part of the capillary. So when the vapor molecules start rising, or they start flying into the capillaries, then because they have these positive, negative sides, they will start sticking to the wall fabric because of these surface charges. And this will create, this is a water retention mechanism. The moisture starts accumulating inside the wall fabric initially as individual molecules, then it will start creating this liquid film, layer by layer, leading to salt movement as well, and leading to non-saturated or saturated capillary movement. The whole moisture accumulation process has to do with these electrical surface charges. That's it, nothing else. That's pretty much the mechanism. That's the main mechanism. And if we go back to the previous drawing, we have these surface energies inside the masonry, and then when we have the water evaporation occurring from the ground, we are going to start having a moisture accumulation inside the wall fabric. What is interesting, when we have a wall fabric which does not have any moisture barrier, so it's a plain stone or a plain brick with lime mortar, so we cannot really remove anything else, the moisture starts accumulating inside the wall fabric because on the account of these surface energies or surface charges, and acts as a moisture accumulation mechanism. Now, we have done some tests in this regard, some detailed tests in the lab, and one thing which needs to be clarified at this stage is that we have two types of wetting in a damp masonry. First, we have on the upper part of the wall, we have the rainwater ingress. We have rainwater hitting the wall fabric. And because the rainwater does not contain salts, it's just the distilled water coming from the sky, then the surface energies are relatively low. The water molecules obviously have a plus-minus charge, but that's it. On the other hand, when we look at the lower part of the wall, typically the lower 1 meter is the rising damp zone, we are dealing with a mix of water and salts. Salts are very interesting and they are a game changer. Salts are otherwise solid materials, like this is table salt made of sodium and chloride. They have a crystalline structure. However, when they are diluted by water, the water will strip the various components of the salts together, and the individual components carried by the water, they will carry electrical charges. They are called ions. So we are going to have a positive sodium and a negative chloride ion. The salts, because they are electrically charged materials, the presence of salts is going to significantly increase these electrical charges inside the walls, or is going to significantly increase the surface energy of the walls. If we refer back here to this drawing here, or sketch, is we can see that the salt molecules are very, very large, and then because they possess electrical charges, they basically will retain a lot of water, they will cluster a lot of water, and the water which normally could fly back and forth and possibly detach itself from the capillary surfaces if the building is heated and ventilated. So despite of these surface charges, applying a bit of extra energy from outside once the wall is damp, for example, we have rainwater, we have these clean molecules which contain no salts, they actually end up in the building fabric temporarily, but once we start actually putting a bit of energy into the wall fabric, either by heating, solar energy, or by just ventilation, kinetic, mechanical energy, this will going to strip the water molecules from these charged surfaces, and the wall is going to dry out. So rainwater is a very, very reversible process because the water comes and goes. In the presence of salts, things change significantly because salts the salt ions contain large, significant electrical charges, and they start clustering these water molecules. So in the presence of rising damp or salt wetting, the water, even if you start applying heating or start applying ventilation in the building, the water is not going to go anywhere, or it's going to go away significantly slower. And we have done, we can quantify this, and we have done a lot of research in this regard. We have done an experiment here testing in a controlled environment 2 bricks. One was very, very salty and the other one was not salty at all. Surface charges can be measured in the masonry. For example, The surface charges associated with the tap water are anywhere between 20 to 40 millivolts, very, very small amounts. On the other hand, the salty wall fabric, the surface charges are multifold, anywhere between 140, 60 to about 240, so about what, 5, 6 times higher. So this just shows that once we have these high surface charges in the wall fabric, the water is much more difficult to strip the water molecules away from the fabric. Going back to this experiment here, we are also measuring the weight gain and weight loss of the wall fabric as we were going through subsequent drying and wetting cycle. These two trays, as you can see here, they are lifted from the ground and they are sitting on a scale, a custom built scale. We have the scale amplifiers here, these blue bits here. And once the bricks are getting drier or wetter based on various conditions from the environment, we can quantify how much water goes into the wall fabric and how much water comes out of the wall fabric, because the weight of the wall fabric or the weight of the bricks changes. What we noticed is that if we keep these bricks in a damp environment by putting a lot of vapor in the environment, a non-salty 2.5 kilo brick collected about 30 grams of water. And in a couple of days, it came back to normal. The salty brick, on the other hand, collected about 140 grams of water under the same conditions, and it took significantly longer, I think about 8 to 10 days, until it came back to normal. So if I'm looking here, basically it says that the salts trap more moisture because on the account of the surface charges, and they can retain 4 times more moisture. Now this is significant. A salty wall fabric retaining 4 times more moisture than a non-salty wall fabric. And the relaxation time is 7 times longer. So a damp salty wall fabric dries out significantly slower and stays wet for significantly longer than a non-salty wall fabric. So going back here, then we can conclude that these surface energies affect the breathability of the wall fabric, are going to make the wall fabric significantly less breathable. And rising damp differs significantly from rainwater. It's a different type of wetting, while rainwater evaporates out quickly, and if the wall fabric is breathable, then the fabric recovers quickly. In the presence of rising damp and in the presence of salts, because of the high surface charges, even if the wall fabric is left breathable, it's not going to dry out as quickly. Actually, the dehydration time is going to be several times slower. And then if you keep adding to this the ongoing moisture, because this is, we are talking about a real wall, not a lab, and the vapors keep rising from the ground and keep being trapped by these salts, it means that in the presence of rising damp, breathability alone is not going to do too much to the wall fabric. The wall fabric might appear dry near the surface, but it's not going to be dry inside the core. And when you remove the moisture barrier, for example, a cement plaster from the wall, yes, the water is going to pool here. You're going to get a lot of moisture here because the vapor movement is stopped. However, removing the moisture barrier, the cement from the surface, within a few days the surface is going to become dry, but under the surface, because of the surface charges, the wall fabric is still going to stay damp for a long time. Now, putting it all together, how can the magnetic DPC deal with the rising damp? How can it affect the rising damp non-invasively? Quite interestingly, in a simple sentence, is by reducing the surface charges of the masonry. If the masonry surface charges, these somehow, by some technical way, are reduced, then it means that the water molecules are not going to stick to the wall fabric. So in theory, if we can completely nullify these surface charges or surface energies, then the water molecule which is coming in at the bottom of the wall just flies in, goes back and forth, maybe bounces back and forth, and exits on the other side of the capillary without being stuck in the wall fabric. And that's exactly what happens. The magnetic DPC will reduce the surface charges, and then the water inside the wall, layer by layer, it will start leaving the building fabric. The surface charges reduce, the bonding here is going to be weakened, and then the top layer is going to peel off and evaporate out of the wall fabric. Then the next layer, and then the next layer, and then the next layer, until the building reaches normal air dry value. And at that point, even if we have ongoing evaporation from the soil and there's no physical damp-proof course to stop the water, because the surface charges are less, this water after that is not going to stick to the wall fabric, or the amount of moisture inside the wall is just going to become normal. This whole compounding effect which occurred in the past is not going to happen. So once the wall dries out, with the magnetic system is going to stay dry and is going to stay breathable, and it prevents the accumulation of the wall fabric due to the presence of the surface energies or surface charges. How can the magnetic damp-proof course change or decrease the surface charges of the wall fabric? What we found that the surrounding electromagnetic environment is affecting the wall fabric, and these surface charges to a large extent are also driven or determined by the intensity, if you wish, of the electromagnetic fields around the walls or just around the building. If you look at the environment, the house is part of the environment. So let's say if you would have a house here, this is part of the overall greater environment. Fields, Earth has a magnetic field, there are also man-made electromagnetic fields, and the house is part of the electromagnetic environment. And what has been found is that the electromagnetic environment is affecting the wall fabric. We have done some studies in this regard, and by the way, this is an almost completely untapped part of building physics or building sciences, and we've just barely started scratching the surface with this, but I show you the data. Hopefully it will make sense. What we have here is we had a building, we are looking at the surface charges. Here it shows 30 some millivolts in that particular wall section, and we're also taking magnetic readings from the environment. So what we see, the orange line, is basically shows some of the changes a few meters away from the wall. And what we noticed that there are all sort of smaller ongoing changes in the magnetic environment. And what we see in the airwaves around the building, it replicates exactly in the wall fabric. The wall fabric almost behaves like, I don't know, like a collector of energy in a way, or an antenna or an aerial or whatever you want to call it. Whatever is around the building is being replicated inside the building. So definitely the energy input around the building is affecting the walls. And to make it short, basically the surface charges are affected and driven by the surrounding magnetic fields. When we have higher magnetic fields around the building, then the surface charges increase and the water retention inside the walls increases, or along the capillaries increases. If we can decrease the magnetic changes and lower the magnetic field inside the building or around the building fabric, then the surface charges start decreasing and the moisture content of the wall start decreasing. The wall start letting go some of the moisture content. So there's a cause-effect relationship between the electromagnetic environment around the building and the moisture content of the walls. And the wall is affected not only by the electromagnetic environment, obviously, but is affected by heating. The amount of sunshine or heating is affected by the amount of ventilation or kinetic energy going back and forth, the wind and so on, is also affected by other factors. But all these factors act together. And the magnetic effects around the building or electromagnetic effects around the buildings are also significant. And this is, as I said, it's very little research about this. For example, we can see here that the long-term changes of the magnetic field, and what we have here, this is in orange here, is going almost hand in hand with some of the electrical changes inside the wall fabric. So the orange line is outside of the walls in the environment, and the blue line is inside the wall, and the two are going almost hand in hand, just without going into complexities. And the changes are very, very small here, the magnetic change. We are talking about nano Tesla order of changes. It's very, very small, but also the changes inside the wall fabric are relatively small, and large and small at the end of the day are all relative values. It means in comparison to what? For example, these tiny electromagnetic changes inside the wall fabric, a few nanotesla here and there, to the human body, to a 50 or 70 or 80 kilogram human body, or 2-meter human body, it's nothing. You can't even feel it, it's nothing. However, in comparison to a 0.1 nanometer water molecule, which is about 10 zeros apart, basically a billion times smaller than the human body, that's significant. So that's the whole point. It's not significant to the human body, but it's highly significant to the water molecule. And I have done some calculation just to put it in perspective. For example, what is the size difference between a water molecule, 0.1 nanometer water molecule, to a golf ball and to planet Earth? And it's kind of about the same. Basically, the size difference between a water molecule and the golf ball is the same relative size difference between the golf ball and a planet Earth. And what the magnetic system fundamentally does, collects energy, collects the electromagnetic energy, drains the environment of its electromagnetic energy, and then through an earthing connection is actually disposed of, sent into the ground. So it means that the energy which is inside the room, around the building, is going to become a tiny bit less. And this tiny bit less is enough to make a difference. What is inside these magnetic DPC systems? Inside the units we have special spiral antennas. And what these do, they collect energy from the environment. Antennas, or aerials, they collect energy. They are energy transforming devices. They pick up energy from the environment, and then they transform it into normal voltages and currents, which are utilized in the mobile phones, in the TV radio industry, and so on. So it's an energy converting device. And what we do, we collect energy with these antennas inside a protective case. And this energy, here's a photo of the real device, you can see the spiral antennas on both faces of the circuit board, and we have a number of them. And this energy once it's collected, is sent to the ground. So fundamentally, we drain the airwaves from some of its magnetic energy. The changes in the wall fabric are measurable with magnetometers, for example. Here is one of our test setups. We are measuring the moisture content of the wall fabric here. This is a real building where we're actually testing the effect. We have some special microwave humidity sensors measuring the moisture content of the masonry. This is the data logger, collecting data every 15 seconds, monitoring any fine change of the masonry. We monitor the depth content of the masonry, we monitor the surface content of the masonry through these surface sensors. We also monitor here some of the electrical parameters. We have these nails and screws inside the wall fabric taking readings of the surface charges or any changes in the electrical surface charges in comparison to the ground, the amount of rain and everything else, the external environment. And then we installed the magnetic systems a few meters away inside the building. As you can see, this is the earthing cable. So the unit is earthed, so collects energy, and the energy is collected in the center of the unit, and through this cable is actually just discarded off. And what we noticed is that once we installed the magnetic unit, here we can see a significant change in the intensity of the magnetic field. Now, what we have here, the drop of the magnetic field is about 2.5 micro Tesla. Now put it in perspective. Earth has a magnetic field. Earth magnetic field varies anywhere between 30 to about 100 micro Tesla. That's kind of the background magnetic field. The magnetic DPC system changes about 2 micro Tesla. So it makes a tiny bit of change unperceptible to humans. And then what was interesting to notice here, this is the drop in the magnetic field with the green line, and then we can see the surface charges also changing at the same time. Once the magnetic field started dropping, the moisture content, the blue of the brickwork, started decreasing at the same time. So recapping the working principle of the magnetic DPC in a couple of sentences, the magnetic system keeps the wall breathable. It increases the breathability of the wall fabric by decreasing the surface energy of the solid fabric, this way letting water to evaporate easier. The bonding mechanism between the wall fabric and the water is reduced, so the moisture content of the wall, the permanent moisture content of the wall can evaporate, making the wall fabric drier. It cannot over dry the wall fabric because there's still moisture movement inside the wall fabric, just like in any normal building which has a solid physical damp-proof. Of course, the vapors are still coming back and forth, it's not a problem. So the wall is going to dry out to normal levels and is going to stay at normal levels going forward. So it actually solves the cause of the problem. I think that would be it about the working principle. Last thing which I wanted to address at the end is a few important questions about basically health, safety and everything else, what can do, because one of the frequent questions we are being asked about the magnetic DPC, or what's going to do to me, to my, I don't know, my pets and my plants and to me and everything else, to bodies. And the simple answer is nothing really. First of all, is because, as mentioned earlier and touched upon this earlier, the changes what the magnetic DPC does are very, very small. They make changes at the level of the water molecule, but the magnetic changes, the decrease it does, it's very, very small on one hand. On the other hand, we have to understand one important thing. The magnetic DPC is not generating anything. A mobile phone is a receiving, transmitting device. It can receive energy and it also can transmit energy, and that's why it's in a two-way communication with the towers. The magnetic system is only receiving energy and takes this energy and gets rid of this energy through its earthing connection. So it means that whatever electromagnetic influences in the building, this is going to make it less. So if you are sensitive to electromagnetic fields and stuff like that, the only effect this is going to have is probably a beneficial effect, because it's going to make the whole living environment less polluted electromagnetically. The systems, by the way, have been tested thoroughly, and here I just show you on the screen, we have it on the website, it's public information. The EC or CE Declaration of Conformity. The system has been tested for all sort of electromagnetic output and passed all the tests. It's not creating anything. I hope I was able to give you some insight into this exciting technology, put some of the doubts and some of the confusion at rest through this video. And if there are any questions, you have any questions, feel free to get in touch with us. You can find us online on coreconservation.co.uk. We have a lot of contact details on the website. And if you like this video, or if you like our content, please don't hesitate to subscribe. And yes, thank you for watching and see you at the next video.